We'll just add to it with more graphs. Do you need more graph paper for notes or anything at all, or are we all right?
I don't know why. I feel like this.
You made cross-country stuff.
I wasn't even looking at how you
That's awesome. Congratulations.
I woke up and it was like 10. I was so
Yeah, we're trying 30, like, so long.
You want to hear about my night? I slid on black ice. Like on my car. In my car.
Cube root functions.
Freaked out. I called my
I've never trusted you to drive me.
I was going on the highway and all of a sudden I like slide and
So when we look at,
and then my dad called me and was like,
excuse me,
oh yeah,
when we
you
look
slid
at,
on black ice.
when we look at cube root functions, we are no longer looking for perfect squares. We're going to look for perfect
Cube.
Exactly. So what you need to think of here are what are going to be your perfect cube roots. 8, good. You have
1, 8, 27.
So we're going to have 0, 1, 8, 27. Now, our normal 10 by 10 grids, are we going to be plotting x equals 27?
No.
No, so we can kind of get rid of that one. But, can I plot negative cube roots? Big old, well, huh? So, let's do this. Let's make our grids for cube roots go negative 8, negative 1, 0, 1, and 8. Now that looks a lot like when you guys, remember how we did the negative 2, negative 1, 0, 1, and 2? You'd see what was bouncing on both sides of the y-axis. It's very similar to that idea. Sure you don't need any extras? Traffic needs more? Sure. Be more than happy to share. Anybody else need some more? Oh, sure, here, let's share this way with you guys.
Thank you.
You're welcome. So what we do here is we're just going to plot these and see what happens. So, oh, excuse me. So what's the cube root of negative 8? What you look for? I don't have it. You want to grab the fish and run to the bathroom and grab the toilet paper? Sorry, I don't have any. So the cube root of negative 8 is, cube root of negative 1 is, cube root of 0, cube root of 1, and cube root of 8. Now when I say cube root, don't think I'm saying cubert, which was an old video game that you had to go up on triangular squares. You don't remember cubert?
No, never heard of it.
Yes, he was in that one. I totally forgot about it. Wreck-It Ralph's a fun movie. And now it's just a matter of,
The new one where all the aliens come to Earth
Oh,
as video games. Pixels. There you go.
then the other thing is then, it's just a matter of plotting it. Negative 8, negative 2. Negative 1, negative 1. 0, 0. 1, 1. 8, and 2. So your cube root function does that. Hey, it looks kind of like the cubed function, but it fell over and flipped. Yes, I had to think about that. Okay. So that's your generic form of what a cube root function is always going to look like. It's the cube root function will not have restriction upon its domain. The reason that it doesn't have restriction upon its domain is because you can take the cube root of any negative number. So the domains for cube roots is going to be all real. Also, if you look at the way that the cube root function works at the tails here are, if you think about it, they're pointing to the left and to the right, but aren't they still pointing up and down, left and right?
Yeah.
They're still increasing. Is there going to be restriction upon the range? Domain and range for cube root function is also all real. There's no restriction upon it. You're always going to be able to take the cube root of something and get some crummy number. No matter what that number is, it will always have a cube root. Okay? So you don't have to worry about, you really don't need to worry about finding domains and ranges with these. Now, just like we did yesterday, well, I tried to do yesterday with that whole number sense thing, which kind of, it went over as about as good as a Led Zeppelin would have.
No.
Why do you guys hate me? I know you're the president of the fan club. But we didn't want to designate it as a hate group because those aren't nice. The anti-Murphy. So, what do you think your A, H, and K is going to do to all these points? The same. Your A is a scalar. That A is that scalar. If there's a multiplier up in front, it might be a 2, which means it could, instead of being kind of level-ish, it might increase and decrease a little bit faster. If it's a fractional amount, it might lower it down. If it's negative, it'll flip it. It reflects it around. H and K, then it's the same deal. Moves it left and right. K goes up and down. Okay. From there, it's just a matter of identifying those points. Always plot your parent graph like we did yesterday, eventually. Plot that A cube root x, and then just move your H and K. So when we do this, let's try an example. Let's say we have y equals -3 cube root x minus 2 plus 4. So, just like we've started every other problem, any of these types of graph problems, whether it's cube roots, square roots, like I said, eventually we get to logarithmic, exponential, trigonometric, whatever, you're always going to want to label out your A. Eventually we'll talk about A, B, H, and K as well, because it's going to help you to find different parts within the graphs. It's so important when we start talking about trigonometry because you're going to have amplitudes, you're going to have period value, you're going to have horizontal vertical shifts within terms of pi, so you have to be able to work with some fractions here and there. But that's still a few months away, but I'm letting you guys know that eventually this whole idea of fractions and knowing how to take half of a half, half of a third, things like that come into play. So here we start out with our A value is -3, my H value is 2, and my K value is 4. So with a positive value of 2, what direction is my graph going to move? Which way? Ooh. Right. It's positive, so it's going to go to the right.
Go right.
So it's going to go to the right, and it's going to go up. So when I do that, I might just put a couple of quick little arrows, just so that way I don't make a silly mistake. And now I just go ahead and plot my parent function. So the parent function is going to be y equals -3 cube root x. Make a quick little table. -8, -1, 0, 1, 8. So now I'm going to get the cube root of -8 was -1. -1 times -3 is how much? Huh? Oh, thank you, I was getting ahead. The cube root of -8 is -2. -2 times -3 is cube root of -1 is -1. -1 times -3 is, next one is, and I plot my parent. Notice by that A value being negative, instead of our generic form where it was increasing from left to right, now it's decreasing from left to right. because of the reflection of the negative there.
Wait, what do you do with the H and K?
We'll plot that last.
Oh, yeah.
We're gonna put the parent function in first, and then we just shift all these 5 points. It's easier to do it that way than what we tried to do yesterday by using the number sense by just picking values. Some people picked up on it pretty quick, but it's not the end of the world for right now. We'll get better at it.
Wait, did you have to do the parent if you just like put stuff in the, like what you thought the square was? If you knew it was like 3, if it was like +1 and you put in 3 and then you put in like 6.
That's fine. I have no problem with that at all because you're using number sense, which makes me happy. On the test, I will ask you guys, I'm trying to make it easy on you, so you don't, because I probably won't use the calculator. Use the parent, because then once you know the parent, you can do, square root of 4 is 2, you can multiply that by a -3 and do all that without racking your brain too much. By doing that, it'll be easier. So, plus parent functions, Julie, doing what you did is awesome. That's great. I hope everybody tried to do it with number sense. My goal is that you guys can do that right off the top of your head. But knowing how to make a parent function, obviously these are really easy to make, is going to help us out so much next semester when we get to a little bit more complex graphs. Okay. So we had -8, -1, 0, 0, 1, -3. And then you can start to see how this one just kind of, by that scalar, it just moves itself. It makes the graph just widen itself out. So this one is the parent function, doesn't technically exist. Our H and K was 2, 4. So now I just plot the real one now. Over 2, up 4. 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 And this one exists, so we don't. And there we are. I'm going to ask you guys to draw the parent, because I want you to practice the parent function, just like I was saying with Luke. I know that you can get away without doing it. I want to make this one easy on you guys, so by asking you to put the parent in, it really makes it pretty straightforward. It takes a second or two longer to do that, but you're really hard pressed to screw up. That's my goal on this one. And just like I was telling Julie, second semester we do a little bit more graphing with a lot of the different functions that we come up with, logs, exponent, exponential, natural logs, and especially trig. Knowing how to plot a parent function is going to be so important because it makes it easier. And some of those get pretty complex, but if you get the grasp of the idea of what a basic function looks like, the rest of it's easy. Do you want another example? Okay, I didn't think so. So what I've already done, and as you might have well aware, I've emailed out a review. Hopefully, maybe some parents got it. Your mom replied. She thought it was very funny. Yeah. So I do that from time to time when I email things out. I did that a few years ago, and Izzy Hayes' mom got the email, and she literally cut and pasted a bunch of stuff all over the place. And they were in, she opened up the fridge, they were in there, they were in her pantry where the food was. And
Wait, where what?
It was on the
that's great. Yeah, that was pretty good suggestions there. So I've already had that uploaded on the calendar. You guys all got an email of it. So what I want to do today is just give you guys a couple of these. I can't imagine the graph and the cube function is going to be tough. So I'll give you a couple of those. But if you don't, or if you have not already printed out the copy of the review stuff, I made some. Yeah, Rasmus. Rasmus.
You use, I have from all of first semester and then post
He's-
all of the
he's
presents
not-
for Christmas.
That's good.
Wait,
So
isn't
I
it the
wake up
same
at, like-
stuff we just printed out last night?
Because you print it out, you get a snarky face.
Sorry, I just looks like the same thing.
Yeah, it's the same thing.
Are you serious? Why did I print it out then? That was a waste of ink.
It's for your parents so they can put it all over the house.
Okay.
So, aside from having to worry about the whole,
Not being able to eat until you figure out the problem.
yeah,
Let's go.
there's a couple of cube root functions on here. Let's just do that. Is that okay? I know that we can make graphing a lot crazier. There are times that I'm not going to worry about hiding values and a values within square roots. I'll worry about hiding those values later on. Well, let's just start working on this. There'll be questions of it on the test. How's that? And I can tell you right off the bat that when you graph, you won't have a calculator.
Yes.
Is this the final review or the review from Monday?
Review for Monday. Okay. So the final review, I'm still working on. Okay. I'm still working on that. If what I want to try and do is, I'm hoping to finish that up sometime this week, and if not, over this weekend, and then that way I can get it to you guys. Yeah, I'll get it to you tomorrow. Sure, I'll give it to you by the end of the day. How's that? No, I should have the actual final review stuff. I'll probably do this weekend, to be honest with you. I'll do the same thing. I'll email it out, make a couple of different PDF files of it. I'll do my best trying to see if I can create them off with this CUDA software again. That way it will have answer guides to it. If not having answer guides, what I'll do over the course, after I post it, I will create an answer key myself with like a worked out solution key. And I'll periodically just update it and just email you guys pictures of my work so you can see the chicken scratch again. When I'm looking at this test then coming up on Monday, the idea is you multiply the numbers together and you make everything positive for x multiplies. So this is 16x to the 7/4 over x squared y squared. Now, what I was asking about is why do you simplify that? Well, the reason that you can simplify this further is because in the numerator, this is more than 1. That's why you can simplify out a value of x. Since 7/4 is more than 1, this is where you have to be careful with top-heavy fractions. That's the exact same thing as saying x to the first times x to the 3/4. I took out 4/4. We okay with that? Which allows me to simplify one of these. That's what happens. Or if you think about it by taking the extra step and play war with the 7/4 and the 2, you would be able to simplify out and then rationalize. But an easy trick to remember is that if you've got whole numbers in the denominator, mixed numbers up top, or I'm sorry, a top-heavy fraction up top, break that down into whole number and fraction, because then you can play war a little bit easier. Okay?
What if like at first you added extremes together, so then I got -1/4, so then I just put the 1/4 on the bottom and multiplied that by 3/4.
And then you got an x and then an 3/4. That's fine. That works
Pretty
too.
much just any time it's like greater than 1 on the top, that's when you have to.
Yeah, you may have to simplify it a little further.
Alright.
When you play with war, you subtract, because x squared is bigger than x to the 7/4, you subtract that. You would get x to the 1/4 on the bottom.
Right, and then you rationalize and bring it back up. And that's kind of what Julie did here. What she did is she played, she combined like terms right off the bat at the top. -2 plus 7/4 is -1/4, brought that down and rationalized up. There's more than one way to do that, so it depends on how you see it and go. Okay? So yeah, then you have simplify, the quick square root style. The awesome ones in the second page, those are your favorites. Inverse functions. Hey, I want to show you how to do number 13 real quick. We have not done an inverse that looked like that. When this one printed out, I wanted to make sure that you guys saw this one. No, we didn't do this. We hadn't done one that looks like this yet. Real fast, when you have a negative fraction, does it matter where you put the negative symbol? I usually float the negative to the numerator. It's easier to maintain, to keep it there. So if I'm going to find the inverse of this function, that means I have to flip-flop x and y. So it's h of x, that plays the role of y. So I'm going to change this to equal x. I'm going to change this to equal y. And now I have to resolve. So the first thing you'd have to do here is move the 1. How do you move a positive 1? Subtract it. So you have x minus 1 is negative 2 over y minus 1. Now, this is fraction equal fraction. You okay with that?
Wait, why did you divide it by 1?
I didn't. Oh.
Oh, wait, no, just
I-
kidding. Sorry.
What happens here is you need to get this y out of that denominator, that y minus 1 out of the denominator. Remember the rules of fraction equal fraction?
Cross multiply.
If you cross multiply, basically what happens here is these two can change spots. Remember rules of ratios from last year with similar triangles? Watch this. If you have 2/3, isn't that the same as 4/6?
I mean, a little bit.
Well, it is. Now, if I change them on the diagonal,
Slightly.
6 over 3, isn't that the same as 4 over 2?
Yeah.
Rules of proportions. When things are proportional, it means they are fraction equal fraction. You can exchange things on the diagonals and it doesn't change it. Now, in essence, it's the long form of doing this. Yes, you cross multiply, you get x minus 1, y minus 1 equals negative 2, which means you divide it by x minus 1. And basically what I've just done is that with one less step. You can change it with the diagonal. I know. So now you get
It has
y minus 1 is that, and then I gotta move that minus 1 by doing what?
Add it, that's exact same property.
And there's its inverse.
That's the problem, though.
I know.
It's its own inverse.
Exactly.
It doesn't make any sense.
So it's just the same.
Wait, if it's the same thing, do you have to show all that work?
Does it always happen like that?
I don't know.
No, I just wanted to show you guys what happens if you have something on a diagonal, that's all.
Well, what if you get a problem like that, but like the x minus 1 and the y minus 1 like don't add up?
Then you just still cross multiply. You still can exchange them. You still just change them on the diagonal. It doesn't matter. If it's,
But if it's like, what if you said if they matched?
it doesn't, I don't mean if it matches here. So it's, you're worrying if this, so if it's 3 over y plus 2,
Yeah.
and you need to get y by itself, you still change on the diagonal. You get y plus 2 is 3 over x, and then you subtract 2.
Oh, really?
That's all it is.
Oh, so you can always just flip them?
Yeah. That's the rule of proportions. 2/3 is 4/6. Change them on the diagonal, and you still get a true statement. You can go the other direction too. You can say 2/4 is the same thing as 3/6. You can flip them on either one of the diagonals, and it's still a true statement.
Murphy,
Yes, ma'am.
it says before t, at negative 1 x is 3 over x plus 2.
They floated the negative to the bottom. If you distribute the negative from the top, you get the same answer. And that's why I usually keep the negative in the numerator, because it's floating. It's this. It means the same result.
Okay, so it's the same thing with
Yeah. Yeah. It means the exact same.
Okay.
Other than that, you get those nasty other ones.
Why did they put x?
There's some f of g ofs and x's and all those are thrown in there. Yeah, try to knock out as much as you can over tonight. And we'll go through, we might be able to go problem by problem with it tomorrow and go through a lot of it. If you guys want, I can try and make a secondary one and post that one through as well, a couple extra problems if you want.
Mr. Murphy, this is on.
It's review, but I'm gonna go over it, so I'm expecting that you do it.
I won't be here tomorrow.
Well, watch the video, so you'll see the review. The internet is your friend.